In the quiet city of Copenhagen, Denmark, in the year 1885, a child was born who would one day change humanity's understanding of the universe. His name was Niels Henrik David Bohr. He entered a world standing on the edge of transformation, both scientifically and socially. The late 19th century was an age of invention and discovery, but it was also an era of curiosity and doubt. Machines were redefining human labor, electricity was beginning to illuminate cities, and scientists across Europe were unlocking secrets that had once belonged to myth and mystery. Yet the true nature of matter, energy, and life remained hidden. Into this restless age of ideas came Niels Bohr, whose mind would grow to challenge the very structure of reality itself. Bohr's childhood was shaped by an extraordinary atmosphere of intellect and culture. His father, Christian Bohr, was a respected professor of physiology at the University of Copenhagen, known for his pioneering work on respiration and the role of carbon dioxide in the human body. Christian Bohr was not merely a scientist, he was a thinker, a teacher, and a man of deep curiosity about how life sustains itself. His home was often filled with students, scholars, and discussions that ranged from philosophy to science to the moral purpose of discovery. Niels, from an early age, grew up surrounded by these ideas. The dinner table conversations were not about trivial matters, they were explorations into the nature of life, the workings of the human body, and the mysteries of existence. This environment nurtured his natural inquisitiveness. His mother, Ellen Adler Bohr, came from a distinguished Jewish family deeply rooted in the world of education, business, and social progress. Ellen brought warmth and culture into the Bohr household, ensuring that her children's minds were not only disciplined by logic, but also enriched by empathy and imagination. She encouraged Niels and his siblings to read widely, to listen to music, and to see beauty in the order of nature. From her, Bohr inherited his quiet demeanor, his patience, and his ability to listen deeply before he spoke. These qualities would later define his unique style of teaching and debate: calm, thoughtful, and profoundly respectful of others' ideas. Growing up, Niels was not the kind of child who drew attention through loud brilliance. He was introspective, observant, and curious. His teachers noticed his exceptional memory and analytical ability, but also his hesitancy to accept answers without questioning them. He was fascinated by the patterns of light, the behavior of water, and the shapes of objects. Simple observations often became long reflections in his mind. He could watch a stone skip across a pond and wonder about the laws that guided its motion. These were not just playful thoughts, they were the seeds of a lifelong desire to understand nature at its deepest level. The late 19th century in Denmark was a time of optimism. Copenhagen was becoming a hub of learning and innovation. The University of Copenhagen, where Bohr's father taught, was a place of vibrant scientific discussion. Niels would often accompany his father to the university, absorbing the atmosphere of academic seriousness that surrounded him. He listened as students debated theories of biology and chemistry, and though he was still a boy, he felt the pull of scientific inquiry. These experiences built in him a sense of reverence for knowledge and a belief that science was not just a career but a calling, a way to contribute to the progress of humanity. When Niels entered Gammelholm Latin School, he quickly stood out for his intellectual discipline. The school emphasized classical education, languages, history, and mathematics, but Niels found his deepest interest in physics and natural philosophy. He was particularly drawn to the works of Isaac Newton and James Clerk Maxwell, whose theories of motion and electromagnetism described the physical world with astonishing precision. The harmony and logic of mathematics appealed to Bohr's mind. Yet, even as a student, he sensed that the world might not always fit into neat equations. There was something mysterious, something beyond what numbers alone could capture. This tension between logic and mystery would follow him throughout his life. Bohr's early experiments began not in a grand laboratory, but in his father's physiology department. When he was still a teenager, he took part in an academic competition sponsored by the Royal Danish Academy of Sciences. The challenge was to measure the surface tension of water using precise methods. Working alone after school, Niels transformed a small room in the physiology lab into his personal workspace. With limited equipment, he improvised instruments from glass tubes and household materials. His younger brother Harold often assisted him, helping with measurements and calculations. Together, they worked with the quiet determination of true explorers. Niels displayed remarkable patience, repeating his experiments countless times to ensure accuracy. When he finally presented his results, the judges were astonished by his meticulous work. The paper he submitted was later published in a scientific journal, a rare achievement for a student still in school. It was his first step into the world of serious science. This early success revealed not just Bohr's technical ability, but his temperament as a scientist. He believed that truth required both precision and humility. He often said that every experiment was a dialogue with nature, and one must learn to listen before trying to speak. This attitude became central to his scientific philosophy. Even in later years, when he led teams of brilliant physicists, he encouraged debate, questioning, and shared exploration rather than rigid authority. Science, to him, was a collaborative journey toward understanding, not a competition for recognition. After completing his schooling, Niels entered the University of Copenhagen in 1903. It was a time when physics was at a crossroads. The old Newtonian laws still reigned, but cracks were beginning to appear in their universal certainty. New discoveries, radioactivity, the electron, and the mysterious radiation emitted by heated objects, suggested that the classical view of the world was incomplete. The atom, once thought to be indivisible, was now being revealed as a complex, dynamic system. Bohr was drawn to these mysteries like a magnet. He studied mathematics, physics, chemistry, and philosophy, building a foundation that blended logic with reflection. At the university, Bohr studied under Christiansen, a leading Danish physicist who specialized in optics and the behavior of light. Christiansen was an excellent teacher but not particularly experimental or revolutionary. Still, his rigorous approach to problem-solving shaped Bohr's scientific discipline. Bohr learned to appreciate the balance between theory and observation, between elegant equations and experimental evidence. He spent countless hours in the university laboratory, conducting experiments that demanded both patience and creativity. His early university years were not filled with fame or dramatic breakthroughs, but with quiet dedication, a rhythm that would define his entire life. During his studies, Bohr became fascinated with the emerging ideas of atomic theory. The question that haunted him was simple yet profound: what is the true nature of matter? He read everything he could find about the electron, the newly discovered particle that seemed to carry the essence of electricity. He studied J.J. Thomson's plum pudding model of the atom and Ernest Rutherford's experiments on the scattering of alpha particles. But even as he absorbed these ideas, he sensed something incomplete. He knew that the universe's smallest building blocks could not be explained by classical physics alone. There was something deeper, something that defied the rules of everyday logic. His intellectual curiosity was matched by his personality, calm, modest, and deeply thoughtful. He was not a flamboyant student. He did not seek attention or dominance in discussions. Instead, he listened carefully, reflected deeply, and then spoke with clarity that often left others in quiet admiration. His professors noted his remarkable ability to see through complexity, to find simplicity in the most intricate problems. He was driven not by ambition, but by the desire to understand. That quiet humility would later make him a respected mentor to some of the greatest physicists of the 20th century. Bohr's university years were also shaped by his close bond with his younger brother Harold, who became a mathematician of great distinction. The two brothers were inseparable companions, sharing not only intellectual pursuits, but also a love for sports, particularly football. Both played for the Akademisk Boldklub, one of Denmark's oldest football clubs, and Harold even went on to play for the Danish national team in the 1908 Olympics. Their relationship was built on mutual respect and intellectual exchange. Bohr often said that discussions with Harold helped him clarify his own ideas, for mathematics, in his brother's hands, was another form of philosophy, a language that described the hidden patterns of reality. Outside the university, Copenhagen was changing. The Industrial Revolution was reshaping cities across Europe, and with it came new opportunities and challenges. Electricity, telegraphy, and the telephone were beginning to connect the world in ways never seen before. For Bohr, these developments were not just technological marvels, they were symbols of humanity's growing ability to understand and control nature. Yet, he also saw that knowledge brought responsibility. His father often reminded him that science was a moral endeavor, not just an intellectual one. This moral dimension became a guiding force in Bohr's character. He would later face moments when scientific discovery intersected with ethical dilemmas, and it was his upbringing that gave him the strength to choose wisdom over ambition. By the time Bohr began his master's studies, he had developed a reputation among his peers as someone who thought differently. He did not rush to conclusions. He would sit quietly for long periods staring at a blackboard or a notebook lost in contemplation. Then, suddenly, he would speak, revealing insights that surprised even his teachers. His master's thesis, completed in 1909, dealt with the electron theory of metals, a topic that required deep understanding of both theoretical and experimental physics. He tackled complex mathematical problems and designed experiments to verify them, showing the balance between imagination and precision that would later define his quantum work. The thesis was not perfect, and many of his results were difficult to confirm experimentally. Yet, what impressed his professors was his originality. He was not content to repeat what others had done. He sought to connect ideas across different domains of physics, searching for unity in apparent contradictions. This tendency to think in wholes rather than parts would become the philosophical backbone of his later theories about the atom and the nature of reality. In 1911, Bohr completed his doctorate with a dissertation on the electron theory of metals. The work was technically dense, filled with complex equations, but its deeper value lay in Bohr's way of thinking. He questioned assumptions that others had accepted without challenge. When he presented his thesis to the examiners, they found it difficult to evaluate, not because it lacked rigor, but because it went beyond the established framework of understanding. This was a sign of what was to come. Bohr was a scientist who would not simply follow the path, he would redraw the map itself. At this point, the young Danish physicist stood at the threshold of a world about to be transformed. His education had given him not only knowledge, but also a mindset, a way of seeing that combined the precision of science with the humility of philosophy. He had learned from his father the value of questioning, from his mother, the beauty of compassion, from his teachers, the discipline of thought, and from his own experience the power of curiosity. All these influences converged to shape the man who would soon step into the heart of the atomic mystery. As Bohr prepared to leave Denmark for further research abroad, he carried with him the quiet determination of someone who understood that science was not a ladder to fame, but a path to truth. He did not yet know that his journey would lead him to Manchester, to work under Ernest Rutherford, or that his ideas would one day revolutionize physics. But even then, as a young scholar, he felt a deep sense of purpose, a calling to understand the invisible forces that govern the universe. His early life and education had prepared him for that quest, giving him the tools not only to think but to imagine, not only to analyze but to believe. In the years that followed, the seeds planted in his youth would blossom into a revolution of thought. The calm, reflective boy from Copenhagen would become the architect of quantum theory, the philosopher of the atom, and the man who taught the world that reality itself might be more mysterious and beautiful than anyone had ever dreamed. When Niels Bohr completed his doctoral studies at the University of Copenhagen in 1911, he had already begun to glimpse the limitations of classical physics. The theories that had served scientists so well for centuries were beginning to strain under the weight of new discoveries. Electrons, X-rays, radioactivity, all hinted that the world beneath appearances was governed by laws far stranger than anyone had imagined. Bohr's education had given him the tools to sense this coming revolution, but the real transformation would begin when he stepped beyond Denmark's familiar classrooms into the broader scientific world of Europe. At 26, Bohr was awarded a scholarship that allowed him to travel abroad to continue his research. His first destination was Cambridge, England, where he hoped to work with the legendary J.J. Thomson, the discoverer of the electron. For Bohr, meeting Thomson was like touching the heart of modern science itself, yet the encounter proved unexpectedly difficult. Thomson, a man of great achievement but conservative temperament, found Bohr's theoretical style unusual and overly speculative. Bohr, who preferred reasoning through deep contemplation rather than endless calculation, struggled to fit into Thomson's structured laboratory routine. Their approaches to science were fundamentally different. Thomson trusted in data and measurement, while Bohr sought meaning and principle. Within a few months, Bohr realized that his time in Cambridge would not yield the inspiration he sought. But the experience was not wasted. He learned something vital: that true discovery required freedom, the freedom to ask unconventional questions, to follow intuition where logic hesitated. From Cambridge he moved north to the University of Manchester, where Ernest Rutherford was conducting experiments that were reshaping the atomic picture. Rutherford's discovery that atoms possessed a dense, positively charged nucleus had already shattered the old, plum pudding model. Here, Bohr found the environment he had been searching for. Rutherford's laboratory pulsed with excitement and open-minded discussion. Young physicists from around the world came to witness and contribute to this new science. Bohr was welcomed warmly, and his quiet yet penetrating intelligence soon caught Rutherford's attention. Rutherford was an experimentalist of the highest order, energetic, direct, and confident. Bohr, on the other hand, was the thinker, the philosopher, the man who could take an experimental observation and build from it a theory of astonishing depth. Together, they formed a powerful intellectual partnership. Rutherford provided the experimental foundation, Bohr supplied the theoretical insight. He began studying the behavior of electrons in Rutherford's nuclear atom, searching for an explanation of how these negatively charged particles could orbit the nucleus without collapsing into it. The problem was simple to state but impossible to solve using classical mechanics. Every known law predicted instability, yet atoms were stable. Something beyond the known laws had to be at work. During these months in Manchester, Bohr's education expanded far beyond the formal curriculum of physics. He absorbed the spirit of open collaboration, the belief that science progressed through dialogue, not dogma. In the evenings, the young researchers would gather to discuss not only their experiments, but the philosophy of their work, what it meant for humanity to uncover the building blocks of matter. Bohr's gentle voice often guided these conversations toward reflection. He would ask questions that cut to the core. What does it mean to observe nature? Is reality independent of our perception? These were not casual musings. They were the early stirrings of the philosophical framework that would later define his interpretation of quantum mechanics. In 1912, Bohr returned to Copenhagen, newly married to Margrethe Ande Rolund, a woman whose intelligence and warmth would become central to his life. Margrethe was not a scientist, yet she possessed the gift of understanding complex ideas and translating them into clear language. She became Bohr's lifelong partner, not only in domestic life, but in thought. She read his drafts, listened to his explanations, and asked the questions that forced him to express his ideas with clarity. In later years, Bohr would often say that every paper he published had first been tested in conversation with Margrethe. Their partnership embodied the balance that characterized Bohr himself, the union of intellect and empathy, logic and humanity. Settled again in Copenhagen, Bohr took up a teaching position at the university while continuing his research. But his mind was restless. The puzzle of the atom still haunted him. He could not let go of the idea that the stability of atoms must depend on something discrete, something quantized. The works of Max Planck and Albert Einstein on quanta of energy had already introduced the notion that energy could exist only in specific amounts. Bohr began to wonder if the same might apply to the atom's structure, that electrons could only occupy certain orbits corresponding to specific energy levels. He returned to Manchester to share his thoughts with Rutherford, who, though skeptical, encouraged him to pursue the idea. Over the next months, Bohr immersed himself in calculations, sketching diagrams, erasing, rewriting, and thinking long into the night. It was the kind of solitary intellectual labor that demanded immense patience and imagination. In 1913, he finally produced a model that explained the hydrogen atom's spectral lines, those mysterious bright and dark bands that had puzzled physicists for decades. According to Bohr's model, electrons orbited the nucleus in fixed energy levels and could jump between them only by absorbing or emitting discrete amounts of energy, or quanta. This was the first time anyone had successfully merged quantum ideas with atomic structure. The result was nothing short of revolutionary. The Bohr model not only explained experimental data, but also predicted new phenomena. It transformed the understanding of matter from a mechanical to a quantum reality. For a young man barely in his 30s, it was an extraordinary leap. When the papers were published in Philosophical magazine, they quickly drew the attention of scientists across Europe. Some were skeptical, others were inspired. Rutherford, though cautious, recognized the brilliance of the work. The quiet Dane from Copenhagen had done what no one else had. He had provided a window into the atom's hidden world. Bohr's educational journey thus reached its first great culmination. Everything he had learned, from his father's physiology lab to the classrooms of Copenhagen, from the experimental rigor of Rutherford to the philosophical depth of his own reflections, had converged into a single theory. Yet even in triumph, Bohr remained humble. He knew that his model was incomplete. He once remarked that while his theory might be right for the wrong reasons, it offered a foundation on which others could build. This humility was not self-deprecation, it was wisdom born of deep understanding that knowledge is always provisional, always evolving. As his fame grew, so did his responsibilities. In 1916, he was appointed professor of theoretical physics at the University of Copenhagen. He now had the chance to shape not only ideas but institutions. Bohr dreamed of creating a center where young physicists could gather to explore the mysteries of quantum theory free from rigid hierarchies. The seeds of this vision were planted during his early education, when he witnessed the power of open discussion and the value of mentorship. His father's home, where conversation flowed between generations of thinkers, became the model for the environment he sought to build for science itself. In 1921, that dream began to take form as the Institute for Theoretical Physics, later known worldwide as the Niels Bohr Institute. Its guiding philosophy was simple: knowledge thrives in collaboration. Bohr's early life experiences, the moral lessons from his parents, the academic discipline of his teachers, and the camaraderie of his peers, all fused into this vision. He wanted his institute to be more than a laboratory. It would be a community, a meeting place for minds. Scientists from across the globe soon arrived, drawn not just by Bohr's intellect, but by his spirit of openness. To understand how Bohr's education shaped his later work, one must look at the manner in which he thought. He approached problems as living questions, not puzzles to be solved once and forgotten. His early exposure to philosophy and mathematics gave him a dual vision: one eye on precision, the other on meaning. When he taught his students, he did not simply lecture, he invited them into dialogue. He believed that every question, no matter how simple, contained within it the possibility of revelation. This attitude reflected the same curiosity he had as a child, watching sunlight dance on water, wondering about the forces at play. Bohr's formative years also gave him a deep sense of humanity that would become vital during the turbulent decades ahead. The early 20th century was marked by both scientific brilliance and social upheaval, 2 world wars, political extremism, and the birth of nuclear weapons. Through it all, Bohr remained steadfast in his belief that science must serve peace. The moral grounding instilled by his family guided him through moments when many scientists were tempted by power or national loyalty. His education had taught him that knowledge divorced from ethics could become dangerous, and he carried this conviction throughout his career. As he matured, Bohr often reflected on how his upbringing in Copenhagen had shaped his way of thinking. The modest size of Denmark, the intimacy of its academic community, and the cultural emphasis on dialogue and equality all contributed to his cooperative spirit. He was Danish not only by nationality but by philosophy. The Danish idea of fællesskab, community and shared responsibility, was at the heart of his science. He saw the universe itself as a kind of community where every particle, every observer, every law of nature was connected in a web of relationships. This perspective would later lead him to formulate the principle of complementarity, the notion that contradictory aspects of nature, wave and particle, certainty and uncertainty, were not opposing truths but complementary ones. Though this concept would emerge fully only in the 1920s, its roots lay deep in Bohr's early life. His exposure to both science and philosophy taught him that truth could have multiple faces, and understanding required the courage to hold paradox without despair. That ability, to live with contradiction and yet seek coherence, was the gift of his education. The young Bohr, who once improvised instruments in his father's laboratory, had grown into a man who built instruments of thought for the entire world. His journey from curious child to groundbreaking physicist was not a straight line of achievements, but a gradual unfolding of awareness. Each stage of his education added a new dimension: precision, creativity, ethics, and finally wisdom. He learned that to understand the atom, one must first understand oneself, that knowledge is a mirror reflecting the observer as much as the observed. Even after his greatest discoveries, Bohr continued to view himself as a student. Visitors to his institute often remarked that he treated every conversation as a lesson. He asked questions even when he already knew the answers, not to test others, but to explore perspectives. This humility, cultivated since childhood, created an atmosphere where even the youngest researchers felt free to challenge ideas. Bohr's way of learning became his way of teaching. The dialogue that began at his family's dinner table expanded into a global conversation that shaped modern physics. His early life was, in many ways, a preparation for the responsibilities that awaited him later. Guiding scientists through the uncertainties of quantum theory, advising governments on the ethical use of atomic energy, and preserving the unity of science in a divided world. Every choice he made reflected lessons first learned in youth: the value of patience, the necessity of doubt, and the faith that truth, however elusive, was worth pursuing. When we look back at the story of Niels Bohr, it becomes clear that his early life and education were not mere background details, but the foundation of his entire philosophy. The curiosity of a child in Copenhagen, the influence of a scholarly father and compassionate mother, the challenges of Cambridge, the inspiration of Rutherford, all these experiences merged into the creation of a mind capable of reimagining reality. His journey reminds us that education is not confined to classrooms. It is the sum of every conversation, every failure, every question that refuses to rest. In the calm tone of his voice, in the careful phrasing of his arguments, one could still hear the echo of the boy who asked why water ripples, why light bends, why the world behaves as it does. That child never disappeared. He simply grew into a man who asked the same questions on a cosmic scale. Bohr's education was not a path to an end but a lifelong apprenticeship in wonder. As the 20th century advanced, and physics entered realms of uncertainty that defied imagination, Bohr stood as both scientist and philosopher, a man whose understanding of reality had been forged in the crucible of disciplined thought and gentle reflection. His early life was a quiet symphony of influences, family, mentors, friendships, struggles, that composed the melody of his later greatness. Through his story, we see that genius is not born in isolation. It grows in the soil of curiosity, watered by mentorship, nourished by humility, and strengthened by doubt. The young Niels Bohr, shaped by the warmth of his home and the rigor of his education, carried these qualities into the wider world. From that foundation arose one of the most profound minds in human history, the physicist who would not merely study reality, but reimagine it. In the years following his return from England, Niels Bohr stood on the threshold of a new era in science. The early 20th century was a time of tension between old certainties and new mysteries. Classical physics, the proud creation of Newton, Maxwell, and others, had explained the motions of planets and the mechanics of machines with near-perfect accuracy. But in the microscopic world of atoms and electrons, it was beginning to fail. Nature, when examined closely, refused to obey the familiar rules. Experiments revealed patterns of light and energy that defied explanation, hinting at a hidden order governed by laws beyond human intuition. Into this atmosphere of uncertainty stepped Bohr, a quiet, reflective man with the courage to question the very foundation of physical reality. The story of Bohr's atomic model began not with brilliance, but with confusion. Scientists already knew from Rutherford's experiments that the atom was mostly empty space, with a dense nucleus at its center and electrons circling around it. But there was a fatal flaw in this picture. According to classical electrodynamics, any charged particle in motion, like an electron orbiting a nucleus, should constantly emit energy as radiation. That meant that within a fraction of a second, the electron should spiral into the nucleus, collapsing the atom completely. Yet atoms did not collapse, they were stable. The universe, it seemed, was disobeying its own laws. Bohr was captivated by this paradox. To him, it was not a dead end but an invitation, a whisper from nature saying, "Look deeper." He realized that the answer must lie in the new concept of quantization introduced by Max Planck and expanded by Albert Einstein. Planck had proposed that energy was not continuous, as previously thought, but came in small, discrete packets called quanta. Einstein had gone further, using the quantum idea to explain the photoelectric effect, where light could knock electrons loose from metal surfaces. These discoveries hinted at a new kind of physics, one in which energy behaved not like a flowing stream, but like a series of steps. Bohr wondered, could the same principle apply inside the atom? He began to imagine a new world, one where electrons did not move freely as classical particles but were restricted to specific orbits. Each orbit, he proposed, had a fixed energy level. The electron could not exist between these levels, just as a person cannot stand between the rungs of a ladder. When an electron jumped from one orbit to another, it would either emit or absorb a quantum of energy equal to the difference between the two levels. This simple but daring idea explained why atoms were stable. As long as an electron remained in one of its permitted orbits, it would not radiate energy. Only when it transitioned between levels would radiation occur. It was a revolutionary way of thinking. Bohr had essentially declared that the atomic world obeyed its own rules, rules that defied the smooth logic of everyday experience. In his model, energy was quantized, motion was restricted, and certainty gave way to probability. He was not just describing an atom, he was reshaping the concept of reality itself. Yet at first, even Bohr himself was unsure if his theory would hold. It seemed too strange, too detached from the familiar mathematics of mechanics. But science, like nature, rewards courage. Bohr tested his model against experimental data, focusing on the simplest atom, hydrogen. For decades, physicists had observed the hydrogen emission spectrum, a series of colored lines produced when hydrogen gas was excited by heat or electricity. Each line represented light of a specific frequency, but no one had understood why only those frequencies appeared. Bohr's model provided the answer. The spectral lines, he realized, corresponded to electrons jumping between energy levels. When an electron fell from a higher orbit to a lower one, it emitted a photon of light whose frequency matched the difference in energy between the two levels. For the first time, the mysterious lines of hydrogen could be calculated precisely, and the results matched experiment with stunning accuracy. The moment Bohr realized his equations worked was one of quiet triumph. There was no fanfare, no laboratory celebration, just the profound stillness of discovery. He had found a bridge between two worlds, the world of the very small and the world of the very large, the classical and the quantum. When he sent his paper on the constitution of atoms and molecules to Philosophical Magazine in 1913, he knew it would provoke both excitement and skepticism. The paper was published in 3 parts, each building on the last, and within months it electrified the scientific community. For many, it was the first glimpse into a new physics, a physics of discontinuity, of rules that could not be visualized but only understood through mathematics and imagination. The Bohr model became an instant landmark. It explained atomic stability, the structure of spectral lines, and even predicted new ones that had not yet been observed. It offered a framework that linked theory and experiment with elegant precision. But more than that, it introduced a new way of thinking about nature. The universe, it seemed, was not continuous but composed of tiny leaps and boundaries, quantum jumps that occurred without warning or path. The idea unsettled many physicists. It violated the deterministic worldview that had dominated science for centuries. If Bohr was right, then the motion of electrons could not be traced smoothly through time. They simply appeared in one orbit or another, governed not by certainty but by probability. Bohr himself wrestled with this philosophical implication. He was trained in classical reasoning, yet his discoveries forced him to embrace paradox. He once remarked that anyone who was not shocked by quantum theory had not understood it. For him, the atom was a symbol of the universe's dual nature, logical and mysterious, measurable yet unknowable in full. He did not see his model as the final truth but as a step toward deeper understanding. In that humility lay his genius. The reactions to Bohr's work were mixed. Some hailed him as the new Copernicus of atomic theory. Others dismissed his quantized orbits as mathematical fiction. Even Rutherford, though proud of his protégé, confessed that he found the model too fanciful. Yet as experimental evidence mounted, resistance faded. The Bohr model accurately predicted the energy levels of hydrogen and other one-electron systems. It became the foundation upon which later quantum mechanics was built. The young Danish physicist had opened the door to a universe far stranger than anyone had dared to imagine. To truly appreciate the magnitude of Bohr's achievement, one must remember the intellectual climate of his time. Physics had long been guided by the belief that nature could be understood through cause and effect, that every event had a precise, measurable explanation. Bohr's theory shattered that illusion. He showed that on the atomic scale, reality behaved differently, that energy changed not continuously but in jumps, and that certain properties could not be known simultaneously. Though the full implications of this would only be realized later through Heisenberg and Schrödinger, Bohr's model planted the seed. It introduced the idea that knowledge itself had limits, that observation was not neutral but participatory. The atomic model also transformed technology and human imagination. It laid the groundwork for quantum mechanics, which would later give rise to lasers, semiconductors, and computers. But beyond its practical applications, it altered the way people thought about existence. The universe was no longer a mechanical clock ticking with predictable precision. It was a living tapestry of possibilities, governed by laws that allowed both order and uncertainty. Bohr had not just explained the atom, he had revealed that the smallest particles mirrored the deepest mysteries of consciousness and reality. His approach to science was unique. Unlike many theorists, Bohr saw beauty not in simplicity but in complementarity, the harmony between opposites. He believed that truth often lay in the reconciliation of contradictions. This belief was reflected in his atomic model, where stability arose from discontinuity and order emerged from quantum leaps. His mind was a place where reason and intuition coexisted, each illuminating the other. When he worked, he would often pause for long stretches, lost in thought, as if listening to the silence between ideas. His students later recalled that he would speak slowly, often repeating sentences in different ways until the meaning revealed itself. For Bohr, understanding was not about speed but depth. The success of the Bohr model quickly spread across Europe, inspiring a new generation of scientists. Among them were Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger, young minds who would carry quantum theory into its next phase. But to all of them, Bohr remained the moral and intellectual anchor. His atomic model was not just a calculation, it was a vision. It invited others to see the universe as a dialogue between knowledge and mystery. Even Einstein, who admired Bohr deeply though he disagreed with his conclusions, recognized the depth of his thought. Their debates on the nature of quantum reality would later define an entire era of physics. Bohr's atomic model also had profound implications for chemistry. It explained the periodic table's structure and the behavior of elements which had long puzzled chemists. The arrangement of electrons in specific energy levels clarified why certain elements reacted as they did and why others were inert. Suddenly, chemistry and physics were no longer separate disciplines, but interconnected branches of the same quantum tree. The idea that the properties of matter arose from invisible patterns of energy transformed not just science, but the philosophy of knowledge itself. Humanity had begun to see that the universe was unified in ways that transcended language and logic. Throughout this period, Bohr remained modest about his accomplishments. He often emphasized that his model was only an approximation, a temporary framework until a more complete quantum theory could emerge. He compared his atomic orbits to the scaffolding of a building, necessary for construction but destined to be removed once the structure was complete. And indeed, by the mid-1920s, the development of quantum mechanics by Heisenberg, Schrödinger, and Dirac would replace the Bohr model with a more accurate and abstract formulation. Yet even then, Bohr's ideas remained central. His concept of quantized energy levels survived, his vision of complementarity became a philosophical cornerstone, and his spirit of inquiry continued to guide the field. For Bohr, science was never about final answers but about continuous dialogue. His atomic model, though superseded in its details, captured the essence of his philosophy, that understanding nature required humility before its complexity. The atom was not a tiny solar system of particles, but a symbol of coexistence between determinism and uncertainty, between what could be known and what must be accepted. His model was a language through which the universe spoke its first quantum words. When the world recognized Bohr's achievement with the Nobel Prize in Physics in 1922, he received it not with pride but with gratitude. He knew that every discovery stood on the shoulders of others, Planck, Rutherford, Einstein, and that future generations would stand on his. The prize was not an endpoint but a reminder of the journey. In his acceptance speech, Bohr spoke not of personal victory but of the unity of science, of how the pursuit of knowledge connected all human beings in a common quest to understand the world. His words reflected the same humility and vision that had guided him since his youth. Bohr's atomic model remains one of the most beautiful ideas in science, not because it was perfect, but because it was bold. It dared to say that reality might be different from what the senses perceive, that truth might come in fragments rather than continuous waves. It was a leap of imagination as great as any in history. In those fragile equations, written by a quiet Danish physicist, lay the birth of the quantum age, a transformation that would alter technology, philosophy, and the very language of existence. As Bohr looked back on his work years later, he reflected that the model had been not just a scientific breakthrough, but a personal revelation. It taught him that the deepest understanding often comes from embracing uncertainty. To study the atom, he realized, was to study the limits of knowledge itself. Every orbit, every quantum jump, was a metaphor for the human condition, a dance between what is known and what remains hidden. The atom, once thought indivisible, had revealed itself as a universe of mystery. And Niels Bohr, through the quiet power of his mind, had shown that within that mystery lay the key to understanding reality itself. The years following the publication of Niels Bohr's atomic model were a period of both triumph and turbulence. Across Europe, laboratories buzzed with excitement. For the first time, physicists could look at the atom not as an abstract curiosity, but as a structured system with rules that could be tested and predicted. The concept of quantized energy levels had turned an invisible mystery into something mathematically tangible. Yet, even as his theory gained acclaim, Bohr knew it was only the beginning of a deeper transformation. The atom had opened its doors, but inside waited an even stranger realm, one that would challenge every assumption about causality, time, and truth. In Copenhagen, Bohr established what would soon become the intellectual capital of modern physics, the Institute for Theoretical Physics at the University of Copenhagen. Funded partly by the Carlsberg Foundation, it was both a workplace and a sanctuary, a place where young scientists from all over the world gathered to debate, to calculate, and to dream. Bohr's institute was unlike any other. There were no rigid hierarchies, no strict schedules. The atmosphere was one of constant conversation, where the line between work and philosophy blurred into one continuous pursuit of understanding. Every corridor echoed with discussion about electrons, photons, and the strange dualities emerging in nature. Bohr himself served as both mentor and philosopher king. He would listen intently as his students presented ideas, interrupting only to pose questions that pierced to the heart of their assumptions. His manner was gentle but probing, as if he were guiding not just scientific reasoning, but the very thought process itself. Those who came to Copenhagen often found their lives transformed. Werner Heisenberg, a young German physicist, arrived at the institute in 1924. Within months, he and Bohr formed one of the most profound intellectual partnerships in the history of science. Heisenberg's restless imagination, combined with Bohr's deep philosophical grounding, gave birth to a new revolution: quantum mechanics. But before that great leap, Bohr's own atomic model began to show cracks. While it worked brilliantly for hydrogen and hydrogen like atoms, it failed to describe more complex elements. The rigid orbits it proposed could not account for the subtleties of atomic spectra beyond the simplest cases. Electrons seemed to behave in ways that no circular path could explain. Even more troubling were experiments showing that light itself sometimes behaved as a particle and other times as a wave. The classical distinction between matter and energy was dissolving, and with it the certainty of Bohr's elegant picture. The model had served its purpose as a stepping stone, but a new framework was needed. Bohr understood this with humility and foresight. He never clung to his theory out of pride. Instead, he encouraged his students to challenge it. He believed that science advanced not by defending old ideas but by asking better questions. Every valuable human being, he once said, must be a radical and a rebel, for what he must aim at is to make things better than they are. His willingness to dismantle his own creation became one of his defining strengths. It was in this spirit that Heisenberg, under Bohr's influence, began developing the mathematics that would soon replace classical orbits with the abstract language of matrices. A radical new way of describing atomic behavior without picturing it in physical space. When Heisenberg presented his ideas in 1925, Bohr immediately recognized their importance, though he struggled at first to reconcile them with intuition. The two men spent long nights walking through the streets of Copenhagen, debating the meaning of the equations. Out of those conversations grew a new principle, one that would become the philosophical core of quantum theory: complementarity. Bohr realized that the apparent contradictions of nature, the wave-particle duality of light, the indeterminate position of electrons, were not flaws but features of reality. They revealed that nature could express itself in mutually exclusive ways, each true within its own context, but incomplete when taken alone. To understand the whole, one had to accept that opposites could coexist. Complementarity became Bohr's answer to the chaos that quantum theory unleashed. It was not merely a scientific principle, but a profound reflection on knowledge itself. He argued that observation always influences what is observed, that the act of measurement is not passive, but participatory. One could measure an electron's position or its momentum, but never both with perfect accuracy, a concept formalized by Heisenberg's uncertainty principle. Bohr saw in this not a limitation of science but a revelation of reality's deeper nature. The universe, he suggested, was not built to satisfy human expectations of clarity. It was richer, subtler, and perhaps inherently paradoxical. This idea struck at the heart of the deterministic worldview that had dominated since Newton. To many, including Albert Einstein, it was deeply unsettling. Einstein famously objected, saying, "God does not play dice with the universe." Bohr's reply was calm yet firm. Einstein stopped telling God what to do. Their debates, conducted with mutual respect, became legendary. Einstein sought hidden variables that would restore certainty to physics, while Bohr defended the probabilistic interpretation of quantum mechanics. To Bohr, probability was not ignorance, it was the language of nature. The randomness observed at the quantum level was not chaos, but an expression of a deeper order beyond human comprehension. Their exchanges, often conducted during long walks or over coffee at conferences, symbolized the philosophical divide between two worldviews, one seeking absolute truth, the other embracing the coexistence of multiple truths. Even as the theoretical debates raged, experimental physics began to confirm the predictions of the quantum model. The spectral lines of complex atoms, the behavior of electrons in metals, the strange interference patterns of particles, all agreed with the new mathematics. Bohr's original model, though incomplete, had been the crucial seed from which this entire revolution had grown. Without his concept of quantized orbits, there would have been no starting point for quantum theory. It was as if the universe had used Bohr's intuition as a bridge to lead humanity into its most mysterious domain. Bohr's Institute became a haven for this unfolding revolution. Physicists from across Europe, Pauli, Dirac, Born, de Broglie, passed through its doors. They debated fiercely during the day and played music or skated on frozen lakes at night. In the informal warmth of that community, the boundaries between nations and egos dissolved. What united them was the shared pursuit of truth. Bohr presided over it all with quiet grace, guiding conversations more with questions than answers. He believed that communication was the essence of discovery, that ideas gained meaning only when exchanged. His famous pauses, his circular way of speaking, sometimes frustrated his colleagues, but behind them lay a mind constantly seeking synthesis. He once said, "We are suspended in language in such a way that we cannot say what is up and what is down." To Bohr, clarity was not about simplifying ideas but about holding their complexity without distortion. As the 1920s gave way to the 1930s, quantum theory matured into a coherent framework. Schrödinger's wave equation complemented Heisenberg's matrix mechanics, and Dirac unified them in a more general formalism. Bohr watched with pride as his students and peers built upon the foundation he had laid. Yet he also continued to wrestle with the philosophical meaning of it all. What did it mean that nature refused to reveal itself fully? Was reality inherently indeterminate, or was human perception simply limited? These questions drove him not just as a physicist, but as a thinker concerned with the boundaries of knowledge. The coming of World War II brought darkness to Europe and tested the moral fabric of science. Bohr, of Jewish descent through his mother, faced grave danger under Nazi occupation. In 1943, he was forced to flee Denmark in a daring escape across the sea to Sweden, aided by the Danish resistance. From there, he traveled to England and later to the United States, where he contributed to the Manhattan Project. Yet even in the midst of war, his conscience was uneasy. The atomic bomb, a direct offspring of the science he had helped create, weighed heavily on his spirit. He advocated for international cooperation an open exchange of scientific knowledge, warning that secrecy and rivalry would lead humanity to destruction. After the war, he became one of the foremost voices for peaceful use of nuclear energy. His open letter to the United Nations in 1950, titled Open World, called for transparency among nations and mutual trust grounded in shared scientific understanding. Through it all, Bohr never abandoned his philosophical exploration. Complementarity extended beyond physics into ethics, biology, and psychology. He believed that every field of human inquiry contained dualities that could only be reconciled through dialogue. To him, the structure of the atom and the structure of human thought were reflections of the same universal principle. That truth emerges not from certainty, but from the interplay of opposites. This vision gave his scientific achievements a moral and spiritual depth rare among physicists. As he aged, Bohr became a symbol of wisdom to the global scientific community. Visiting researchers described his presence as calming, almost meditative. His home near the Carlsberg Brewery, where he lived as part of the brewery's tradition of supporting scholars, became a meeting place for thinkers from all walks of life. In that house, discussions ranged from physics to poetry, from politics to philosophy. He welcomed everyone with equal respect, convinced that insight could come from any quarter. His laughter was soft, his manner unassuming, but his intellect radiated a quiet intensity that inspired reverence. In his later years, Bohr turned again to the question that had haunted him since his youth: what is reality? He saw that quantum theory, despite its success, offered no simple answer. Instead, it invited humanity to rethink what it meant to know anything at all. Reality, he suggested, might not be a single, objective entity, but a mosaic of perspectives, each revealing part of the truth. Observation and reality were intertwined, inseparable. The atom, once thought to be the smallest and most concrete unit of matter, had become a mirror reflecting the fluid nature of existence itself. In that realization lay both wonder and humility, the recognition that the more deeply we probe the universe, the more we encounter ourselves. Bohr's final years were spent revisiting his principle of complementarity, refining it into a broader philosophy of human understanding. He applied it to the relationship between science and religion, between logic and emotion, between the individual and society. Everywhere he looked, he saw the same pattern: unity through duality, harmony through contrast. He came to believe that peace, whether in science or in the world, could only be achieved by accepting that different perspectives, though seemingly contradictory, could coexist without canceling each other. This belief made him not just a physicist of atoms but a physicist of meaning. When Niels Bohr passed away in 1962, the world mourned not only a scientist, but a visionary who had redefined humanity's relationship with the unknown. His atomic model, once a daring speculation, had evolved into the foundation of an entire discipline, yet its true legacy lay in the spirit it embodied: the courage to imagine beyond reason, to embrace paradox, and to see beauty in the boundaries of knowledge. The atom that Bohr described was not a mechanical system, but a living metaphor for the universe itself, a universe where certainty and mystery dance together in eternal rhythm. Today, every technology that shapes modern life, computers, lasers, medical imaging, quantum communication, traces its ancestry to the principles that Bohr helped uncover. Yet his influence extends beyond laboratories and equations. In classrooms, in philosophy, in art, his vision continues to inspire those who seek to understand not just how the world works, but why it works that way. His insistence that science and humanity are inseparable remains a guiding light in an age still struggling with the balance between knowledge and wisdom. Standing before his statue at the University of Copenhagen, one senses not the grandeur of a monument but the serenity of a thinker who found wonder in every question. Bohr's gaze, sculpted in bronze, seems to look inward as much as outward, reflecting the eternal dialogue between mind and matter. Around him, the world he helped reveal continues to unfold in ways even he could not have imagined: quantum computers harnessing probabilities, physicists exploring entanglement across vast distances, philosophers revisiting the nature of observation. Each discovery, each paradox, echoes his quiet conviction that reality is not a fixed truth but an ever-expanding conversation. And so, the story of Niels Bohr's atomic model does not end with its equations or its Nobel Prize. It lives on as an idea that reshaped the boundaries of thought itself. His atom was the gateway through which humanity glimpsed a deeper order, a universe woven not from certainty, but from possibility. In those invisible orbits, in those quantum jumps between energy levels, lies a reflection of our own journey, the leap from ignorance to insight, from simplicity to complexity, from illusion to understanding. Bohr taught the world that to know reality, one must be willing to reimagine it. And in doing so, he forever changed what it means to see, to think, and to be. As the dust settled after the initial storm of quantum discoveries, Niels Bohr found himself drawn deeper into the philosophical heart of the mystery he had helped create. For Bohr, physics had never been merely a mathematical exercise, it was a profound human dialogue with nature. Every equation, every observation, was a kind of conversation, a question whispered into the unknown, waiting for the universe to respond. Yet the answers he and his colleagues were receiving from the quantum world seemed to defy the very language they used to describe them. The more they tried to picture what was happening inside the atom, the more reality itself seemed to dissolve into ambiguity. Out of this confusion emerged one of Bohr's most profound insights. The idea that truth in the quantum world could not be singular, that reality revealed itself in fragments, each piece valid in its own domain but incomplete when viewed alone. This realization would become the cornerstone of his philosophical vision, the principle of complementarity. The seed of complementarity was planted during Bohr's long discussions with Werner Heisenberg in the mid-1920s. The two men often walked together late into the night through the quiet streets of Copenhagen, their minds ablaze with questions. How could light sometimes behave as a wave and at other times as a particle? How could an electron be said to have both a definite position and an indeterminate momentum? These contradictions tormented physicists, who had long believed that a single, unified description of nature must exist. But the experiments said otherwise. Depending on how one measured it, the same entity, whether light or an electron, could display completely different behaviors. For Bohr, this was not a failure of science, but a revelation about the limits of human understanding. It suggested that the act of observation was not separate from nature, but part of it. That what we see depends on how we look. This idea grew into something vast and transformative. Bohr began to see that the apparent contradictions of quantum theory were not flaws but fundamental truths that coexisted without canceling each other. Just as the two sides of a coin could not be seen simultaneously, yet both were essential to its existence, so too could physical phenomena possess dual aspects that were mutually exclusive yet jointly complete. The wave and the particle were not rivals, but partners in a deeper unity that transcended the language of classical thought. This was complementarity, the understanding that opposing descriptions of a system could both be necessary to grasp its full reality. For Bohr, complementarity extended beyond physics. It was a window into the structure of thought itself. He believed that every act of knowing involved a relationship between the observer and the observed, between the question and the answer. In the classical world, that relationship seemed simple. One could measure a property without disturbing it. But in the quantum world, this separation dissolved. The observer's choice of experiment determined what aspect of reality would be revealed. One could measure a particle's position or its momentum, but never both with infinite precision. Nature offered one face at a time, never the whole. Bohr interpreted this as a profound lesson about the nature of knowledge, that objectivity did not mean detachment, but participation. To know something was to enter into a relationship with it, and every relationship had its boundaries. This redefinition of knowledge unsettled many of Bohr's contemporaries. For centuries, Science had been built on the dream of objectivity. The belief that the universe could be described exactly as it is, independent of the observer. Bohr's philosophy suggested that this dream was an illusion. The universe, he argued, does not simply exist out there, waiting to be measured. It reveals itself through interaction. Observation is not passive reception but creative participation. This was a radical shift, one that blurred the boundary between mind and matter, between human perception and physical reality. In Bohr's view, nature was not a static mechanism but a living conversation, and the scientist was not a detached spectator, but a participant in its unfolding story. At first, many resisted this vision. Albert Einstein, in particular, could not accept it. He believed that the role of physics was to describe reality as it truly is, not merely as it appears through measurement. The idea that fundamental properties might not exist until observed seemed to him deeply unsatisfactory. He and Bohr clashed repeatedly on this issue, their debates becoming legendary. At conferences like Solvay, the two giants would stand before blackboards for hours, exchanging arguments that were as philosophical as they were scientific. Einstein would devise clever thought experiments meant to expose flaws in quantum theory, only for Bohr to respond with calm precision, showing that each scenario still obeyed the principles of complementarity and uncertainty. Their disagreements were never hostile, they were a testament to the depth of their mutual respect and to the seriousness of the questions at stake. In their dialogue, the meaning of reality itself was being rewritten. Bohr saw complementarity not as a limitation but as a liberation. It freed physics from the constraints of absolute description, allowing it to embrace the complexity of the world as it truly is, multifaceted, paradoxical, and alive. He once remarked that, "The opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth." This sentence captured the essence of his philosophy. Truth, for Bohr, was not a fixed point, but a balance of tensions, a harmony between perspectives that could not coexist yet could not be separated. Just as light could not be understood without considering both its particle and wave nature, so too could human understanding not progress without reconciling opposing viewpoints. Complementarity, in this sense, became a metaphor for all knowledge. As the concept matured, Bohr began applying it beyond the laboratory. He saw parallels between quantum paradoxes and the contradictions of human life. In psychology, for example, one could not separate the conscious from the unconscious, both shaped experience. In ethics, freedom and responsibility were not opposites but two sides of the same coin. In politics, authority and liberty needed to coexist in dynamic balance. To Bohr, the quantum world had revealed a universal principle, that wholeness arises not from uniformity, but from the interplay of differences. This insight gave his work a humanistic dimension that set him apart from his peers. He was not just describing atoms, he was describing the logic of existence itself. Within the walls of his Copenhagen Institute, these ideas took on a life of their own. Bohr's students and collaborators found themselves not only studying equations, but engaging in philosophical exploration. Discussions would stretch late into the night, spilling from the lecture hall into the dining room, where plates of food grew cold as debates heated up. Bohr would listen patiently, his head tilted slightly, his eyes distant, as if tracing invisible patterns of thought in the air. Then he would speak slowly in his peculiar rhythm, repeating, rephrasing, circling around an idea until its deeper meaning emerged. To his students, it was both maddening and mesmerizing. They learned that to think with Bohr was to think deeply, to question not only one's conclusions, but the very assumptions behind them. He taught them that clarity was not the absence of ambiguity, but the ability to live within it. Complementarity also reshaped Bohr's approach to language. He realized that the words scientists used were themselves a kind of measurement, tools that shaped what could be said and known. Classical terms like particle and wave were remnants of a world that no longer existed in the quantum domain. Yet new words had not yet been born. Bohr believed that the only way to speak about the atomic world was through analogy, through metaphors that pointed toward meaning rather than captured it completely. This humility before language became central to his philosophy. He understood that words could illuminate but also imprison, that they could describe only slices of a larger reality that forever eluded complete articulation. For Bohr, the challenge was not to eliminate ambiguity, but to learn to think beyond it. As his ideas spread, Bohr's principle of complementarity began to influence not only physicists but philosophers, theologians, and artists. It resonated with those who sensed that the modern world, despite its technological triumphs, was losing its sense of balance. Complementarity offered a new way of understanding complexity, not as chaos but as coexistence. It suggested that opposites could define each other, that contradiction was not the enemy of truth, but its expression. Bohr's insight thus transcended science, offering a framework for dialogue between disciplines and even between cultures. He saw in it a path toward reconciliation, between East and West, reason and intuition, science and spirituality. In the broader history of ideas, Bohr's philosophy marked a profound turning point. Before quantum theory, science had sought certainty, the belief that everything, if measured precisely enough, could be known. After Bohr, that certainty was gone. But in its place emerged something richer, an understanding that knowledge is relational, that meaning arises through context. This shift was not a loss but an evolution. It mirrored the human journey itself, from the illusion of control to the acceptance of mystery. Bohr's principle of complementarity, thus, became not only a statement about the quantum world, but a reflection of the human condition. Even in his private reflections, Bohr approached these questions with humility. He often said that every discovery deepened the mystery rather than resolved it. When asked whether he truly understood quantum mechanics, he famously replied, "Anyone who is not shocked by quantum theory has not understood it." To him, the shock was part of the beauty, the reminder that reality was always more subtle than the mind could grasp. His serenity in the face of uncertainty made him a figure of quiet wisdom. While others sought definitive answers, Bohr found peace in the endless unfolding of questions. In the 1930s and 1940s, as the world descended into political chaos, Bohr's principle of complementarity took on new meaning. He began to see it as a model for human coexistence, a way to bridge the divides that were tearing nations apart. Just as the wave and the particle could not be understood separately, neither could opposing ideologies exist in isolation. Understanding required dialogue, not domination. In this sense, complementarity became both a scientific and moral principle. It taught that truth could only be approached through openness, through the willingness to see from another's perspective. Bohr carried this conviction into his efforts after World War II to promote international collaboration in science. He believed that the lessons of the atom were not just technical but ethical, that humanity's survival depended on learning from the very universe it sought to control. Through all these years, Bohr remained a man of quiet depth. His thoughts flowed slowly but powerfully, like a deep river that never rushed yet carved valleys wherever it passed. Those who met him often spoke of his eyes, clear, reflective, filled with both wonder and gravity. He embodied the same paradox he described in nature, certainty born of doubt, strength rooted in gentleness. To converse with Bohr was to feel the presence of a mind that had glimpsed the foundations of reality and returned with a message not of conquest but of harmony. Complementarity was his gift to the world, not a theory to be proven, but a way of seeing. It asked humanity to embrace complexity rather than fear it, to find unity in diversity, and to understand that opposites are not enemies but partners in creation. Through it, Bohr reimagined not only the atom, but the nature of truth itself. In the quantum world, he revealed, everything was connected, observer and observed, cause and effect, question and answer, all parts of a single cosmic dance that no human mind could ever fully choreograph, yet every mind could join. As the years advanced, Niels Bohr's reflections on complementarity became more intricate, more entwined with the destiny of humankind itself. What had begun as a principle to interpret atomic experiments evolved into a philosophy of coexistence, a vision of how knowledge, ethics, and civilization might endure in an age defined by paradox. Bohr often recalled those long nights in the institute at Blegdomsvage, where chalk dust floated in the dim light as if mirroring the suspended probabilities he spoke of. He would pause mid-sentence, turn toward the blackboard, and draw two intersecting circles, the simplest possible image of complementarity. Here, he would say softly, is the domain of what can be said, and here the domain of what can be known. They overlap, but never completely. His hand would rest between the circles. All our understanding lives in this overlap. To his students, this small sketch carried the weight of revelation. It meant that truth could never be complete, that knowledge was a meeting point between experience and description. Fragile, provisional, yet luminous. In these later years, Bohr became increasingly fascinated by how his philosophical insight might heal divisions beyond physics. He began to see that the same intellectual humility demanded by quantum theory was urgently needed in human affairs. Nations, ideologies, and individuals often sought absolute certainty just as classical physics once had. Yet, Bohr argued, the world's deepest problems could not be solved through domination of one perspective over another. They required complementarity, the acceptance that conflicting viewpoints might each express part of a greater whole. During the 1930s, as totalitarianism spread across Europe, Bohr's quiet humanism took on moral urgency. In letters and lectures, he urged scientists to defend openness of thought, reminding them that the great lesson of atomic theory is the necessity of tolerance. When war erupted, he worked under immense strain. Denmark was occupied, and Bohr, though a political by nature, found himself at the center of moral dilemmas that tested his philosophy in the harshest possible way. In 1941, Werner Heisenberg, his former protégé and now a leading figure in the German nuclear effort, came to visit him in Copenhagen. The meeting remains one of the most haunting encounters in the history of science. Two minds that had once built the quantum world together now stood on opposite sides of a moral chasm. No one knows precisely what was said, both men later remembered it differently. But it seems clear that Heisenberg sought Bohr's understanding, perhaps even approval, for his involvement in the German project. Bohr, deeply disturbed, interpreted the conversation as a plea to legitimize a weapon that could annihilate cities. Their bond was broken. Yet even in his anguish, Bohr tried to see through the lens of complementarity. He recognized that Heisenberg's actions, however misguided, arose from a reality as complex as the particles they had once studied: fear, patriotism, ambition, duty. After the war, Bohr never publicly condemned him. Instead, he turned again to dialogue, believing that healing could only come through mutual understanding. To Bohr, even moral truth required complementarity, judgment tempered by empathy, principle balanced by compassion. When Bohr fled occupied Denmark in 1943, smuggled across the sea to Sweden in a fishing boat, and then flown in a cramped military plane to England, the philosophical became visceral. His escape mirrored the uncertainty he had so often described as a life suspended between states, survival determined by chance. In London and later in America, he joined the Allied effort, advising scientists on the potential consequences of nuclear research. His conversations with figures like Churchill and Roosevelt were cautious but charged with urgency. He warned that the atomic bomb, if developed in secrecy, would endanger the moral fabric of civilization. Bohr's proposal was bold and profoundly idealistic: an open world. He envisioned a future in which nations shared scientific knowledge transparently, preventing mistrust and fostering cooperation. Just as complementarity required communication between differing perspectives, global peace required communication between nations. But the political leaders of the time, gripped by wartime fear, found his vision naïve. The bomb was built in silence, its first light exploding over Hiroshima. Bohr was devastated. The energy he had helped unlock in his theoretical work now illuminated the darkest corners of human potential. In the aftermath, Bohr's philosophy deepened into a plea for moral evolution. He insisted that humanity's survival depended on adopting the intellectual humility revealed by quantum theory. Just as no observer could claim absolute knowledge of a particle, no nation could claim absolute righteousness. He wrote essays and gave lectures urging a new kind of realism, not the realism of power, but the realism of relationship. Every great advance in science, he said, has issued from a crisis in thought. Perhaps, he hoped, the atomic crisis might awaken a global consciousness capable of embracing complementarity as a political and ethical principle. Back in Copenhagen, Bohr resumed teaching with renewed intensity. The post-war years brought a new generation of students eager to understand both the science and the spirit of the quantum revolution. In his lectures, he spoke less of calculations and more of meanings. Physics is not about what nature is, he told them, but about what we can say about nature. This subtle distinction carried the entire weight of his philosophy. It meant that human knowledge was always conditional, that even in its triumphs, science must remain self-aware and humble. He encouraged his students to study philosophy, linguistics, and history alongside mathematics. You must learn to think in opposites, he would say, smiling. Only then can you find the unity. Many who studied under him later became pioneers in fields far beyond physics. In biology, computer science, even sociology, each carrying a trace of Bohr's integrative vision. His influence radiated outward like a quiet field, invisible yet inescapable. During his lifetime, Bohr's home became almost mythic, a place where the frontiers of thought were explored around the dinner table. Guests remembered how discussions would drift effortlessly from atomic spectra to ancient myths. Bohr's wife, Margaret, often rescued visitors from the overwhelming pace of his reflections, translating his cryptic remarks into everyday sense. The rhythm of those conversations captured the essence of complementarity itself, logic and intuition, rigor and warmth, merging into a single act of understanding. In those years, Bohr also turned his attention to biology, intrigued by how living systems might exhibit quantum-like relationships between parts and wholes. He suggested that the concept of complementarity might explain the dual nature of life, simultaneously mechanical and purposive, physical and experiential. Although these ideas remained speculative, they hinted at the vast reach of his philosophy. He was, in a quiet way, attempting to construct a new synthesis between science and the humanities. The depth of Bohr's thinking often made him difficult to summarize, even for his closest collaborators. His words seemed to move in spirals, approaching the heart of an idea through paradox. He once admitted that his writing frustrated readers because it tries to convey a state of mind more than a statement. To truly grasp his meaning required patience, the willingness to dwell in ambiguity until understanding emerged. In this way, he taught not only through argument but through example. By the 1950s, Bohr had become an elder statesman of science, respected, sometimes venerated, occasionally misunderstood. The world was entering the Cold War, and nuclear anxiety shadowed every political decision. Bohr continued to advocate for openness, meeting diplomats and leaders, urging them to see science as a bridge, not a weapon. He reminded them that just as an electron could not be fully described without considering its interactions, so too could nations not exist in isolation. Complementarity was for him the law of survival. His speeches from this era reveal a remarkable blend of physics and ethics. He would begin by describing the dual behavior of light, then pivot seamlessly to the dual needs of civilization, freedom and security, individuality and cooperation. The same logic governed both, he insisted. Only by respecting the interplay of opposites could stability arise. Audiences sometimes left bewildered, unsure whether they had attended a physics lecture or a moral sermon. But Bohr cared little for boundaries. He had long since transcended them. In his later writings, Bohr reflected on the symbolic power of the yin-yang emblem from Eastern philosophy. He saw in it an ancient visualization of complementarity, the interdependence of opposites within a single circle. When Denmark knighted him in 1947 and allowed him to design his own coat of arms, he chose that very symbol, accompanied by the Latin motto Contraria sunt complementa. Opposites are complementary. It was the perfect encapsulation of his life's work, a union of science, philosophy, and universal wisdom. As his health declined in the early 1960s, Bohr remained active, still pondering new questions, still revising old essays, still walking the corridors of the Institute with quiet determination. Those who visited him noticed a serenity that bordered on transcendence. He seemed to have made peace with the incompleteness of all knowledge. When asked if he believed humanity would ever achieve ultimate understanding of the universe, he smiled and shook his head. "There is no ultimate," he said, "only ever-deepening coherence." On November 18, 1962, Niels Bohr passed away in Copenhagen at the age of 77. The news spread quickly through the scientific world. Colleagues and students gathered at the Institute to honor him, their conversations blending grief with gratitude. For many, his death marked the end of an era, the passing of one of the last physicists who had truly united science and philosophy. But Bohr's spirit remained woven into the fabric of modern thought. His ideas continued to shape discussions not only in physics but in fields as diverse as psychology, information theory, and ecology. The principle of complementarity lived on, evolving in new forms wherever thinkers grappled with the tension between opposites. Today, more than half a century later, Bohr's philosophy feels uncannily relevant. In a world fractured by polarization, between nations' ideologies, and even digital realities, complementarity offers a model for reconciliation. It reminds us that difference is not error but expression, that understanding requires the coexistence of perspectives. In quantum mechanics, the observer and the observed are inseparable. In society, the self and the other share the same fate. The lesson is timeless. Truth is relational. Modern physicists still debate the interpretation of quantum mechanics, but Bohr's conceptual framework endures as the foundation of all. Even those who disagree with his philosophical stance must engage with it. It defines the language in which the questions are asked. Every time a scientist designs an experiment to measure a quantum state, they are living out Bohr's insight that what is observed depends on the method of observation. His thought has become the invisible grammar of modern physics, and beyond science, artists, poets, and thinkers continue to find inspiration in his paradoxical wisdom. Painters have invoked complementarity in the play of light and shadow. Musicians have found it in the tension between harmony and dissonance. Psychologists have applied it to the dual nature of the human mind. Wherever opposites seek unity, Bohr's influence whispers. If one imagines a cinematic closing scene to his story, it might unfold like this. The camera drifts through the quiet halls of the Copenhagen Institute on a winter evening. The rooms are empty now, but traces of the past linger. Chalk equations fading on a blackboard, a notebook open on a desk, a cup half full of cold tea. Outside, snow falls gently over the city. The sound of distant bells merges with the faint hum of wind. The lens moves toward Bohr's old office, where a single light glows. On the wall hangs his coat of arms, the yin-yang symbol encircled by the words Contraria sunt complementa. The camera lingers, and the narration returns in a low, reflective tone. He taught us that reality is not one thing or another, but both, that certainty is the child of humility, and knowledge the mirror of our participation in the world. In every observation, something of ourselves is measured. In every truth, its opposite waits to be understood. The light flickers, fades. The screen darkens, leaving only the soft shimmer of possibilities. The eternal dance between question and answer, between matter and meaning. In that silence, Bohr's legacy continues not as a conclusion, but as an invitation to think more deeply, to see more widely, to embrace the unity hidden within contradiction. For Niels Bohr, the atom had never merely been a physical entity. It was a symbol of the human spirit, small, mysterious, indivisible, yet containing infinite potential. Within its uncertain orbit lay the pattern of all existence, the complementarity of being and becoming, of knowing and not knowing, of light and shadow. To understand it was to glimpse, however briefly, the rhythm of the universe itself, a rhythm that spoke not of certainty, but of balance. And so, long after the last equations have been erased, his voice still echoes calm, measured, compassionate. The task of science, he reminds us, is not to eliminate mystery, but to frame it within understanding. In those words, the story of complementarity finds its final harmony, not an ending, but a continuum where every paradox becomes a doorway and every question a beginning. The debates between Niels Bohr and Albert Einstein were among the most profound intellectual confrontations in the history of science. They were not arguments of ego or rivalry, but dialogues between two towering minds trying to understand the true nature of reality. In those moments, the world of physics became a theater of philosophy, where the most fundamental questions about the universe were explored through logic, experiment, and imagination. Bohr and Einstein shared deep respect for one another, yet they stood on opposite shores of a river that no bridge could completely cross. Einstein believed in a universe ruled by certainty and order, a cosmic clock governed by laws that never faltered. Bohr, in contrast, saw reality as more elusive, shaped not only by what exists but by how it is observed. Their story begins in the early 1920s, when quantum mechanics was still forming its foundation. The discoveries of Planck, Schrödinger, and Heisenberg had shaken classical physics to its core. Particles could behave like waves, outcomes could only be predicted by probabilities. Einstein, who had once laid the groundwork for quantum theory with his explanation of the photoelectric effect, was now troubled by its implications. He could not accept that God, as he famously said, plays dice with the universe. To him, uncertainty was a sign that something deeper was missing, a hidden order waiting to be discovered. Bohr, however, embraced uncertainty as a fundamental truth. For him, the quantum world did not obey the rules of human intuition. He argued that the observer was not separate from what was being observed. Measurement itself influenced the outcome. The act of looking changed what was being seen. This was not just a scientific claim, it was a philosophical revolution. It meant that reality was participatory, that the universe revealed itself through interaction, not isolation. Bohr's ideas challenged centuries of thought, and Einstein found them deeply unsettling. Their first great debate took place at the Solvay Conference in Brussels in 1927, where the greatest minds of physics gathered to discuss the strange new theory. Einstein presented thought experiments designed to expose flaws in quantum mechanics, imagined setups where the uncertainty principle might be violated. Calmly, methodically, Bohr countered each one, often staying awake through the night to refine his arguments. The next morning, he would return to Einstein with a quiet smile and a precise explanation. Einstein's ingenuity met Bohr's patience, and their exchanges became legendary. Observers recalled that though their words sometimes clashed, their eyes conveyed mutual admiration. It was as if two mirrors reflected the same mystery from different angles. These debates continued for years, shaping the philosophy of modern science. Einstein's realism and Bohr's complementarity stood like two pillars of thought, each indispensable, each incomplete without the other. Einstein insisted that physical reality must exist independently of observation. Bohr maintained that reality had meaning only through observation. Their discussions were not about winning, but about reaching deeper understanding. The tension between them symbolized the very duality they argued about: certainty versus probability, determinism versus freedom, objectivity versus perspective. By the 1930s, their intellectual duel had evolved into friendship tinged with philosophical distance. They exchanged letters filled with respect, wit, and deep curiosity. Even as Einstein grew older and more isolated in his search for a unified field theory, Bohr continued to expand the philosophical foundations of quantum mechanics. To Bohr, Einstein's relentless pursuit of hidden order was noble but misplaced. The mystery was not a flaw to be solved, it was a feature of existence. Every sentence I utter must be understood as a question. Bohr once said, a reflection of his humility before the unknown. Their most famous exchange came when Einstein proposed the EPR paradox, a thought experiment suggesting that quantum mechanics allowed spooky action at a distance, where two particles could influence each other instantly, even when separated by vast distances. He intended this to prove that quantum mechanics was incomplete. Bohr, after careful analysis, turned the argument on its head. He showed that the paradox was not a failure of quantum mechanics, but rather a demonstration of its most profound truth, that nature's connections transcend classical separation. The experiment that Einstein meant as a critique became, decades later, evidence of quantum entanglement, one of the most extraordinary discoveries in physics. The debates between Bohr and Einstein did more than refine scientific theory, they revealed the human dimension of discovery. Behind the equations stood two men wrestling with the limits of knowledge and the meaning of reality. Einstein sought comfort in a rational cosmos, while Bohr accepted the ambiguity of the unknown. Yet, in their difference lay harmony. Without Einstein's challenges, Bohr's ideas might not have been tested so rigorously. Without Bohr's resilience, Einstein's critiques might have remained unrefuted. Together, they forged the intellectual drama that defines modern physics. In their final meetings, long after the formal debates had ended, the tone between them was gentle and contemplative. They would sit together at conferences, sometimes in silence, gazing at the same blackboard as if listening to the faint music of the cosmos. Their disagreement had become friendship, their opposition had turned into complementarity. It was as if their very relationship mirrored the dual nature of the quantum world. Two distinct entities bound by an invisible connection. Einstein never accepted the full implications of quantum theory, but he respected Bohr's brilliance. Bohr, in turn, revered Einstein's pursuit of truth. When Einstein passed away in 1955, Bohr mourned not an adversary but a kindred spirit. He wrote, "When the great guiding star sets, the sky is never quite the same again." Their debates had illuminated the path for generations of physicists, revealing that science is not merely about finding answers but about asking better questions. In the end, their dialogue remains unfinished, echoing through every laboratory and lecture hall where the mysteries of quantum mechanics are explored. Bohr's vision taught that truth may appear contradictory, but is united beneath the surface. Einstein's conviction reminded us that order and beauty must still exist, even when unseen. The dance between these two ideas continues to define the modern search for understanding. Their debates were not just about particles and equations, they were about the soul of science itself. Through their passion, humility, and courage to question reality, Bohr and Einstein showed the world that knowledge is a living conversation, one that never ends, but forever deepens. When the Second World War engulfed the world, Niels Bohr found himself drawn into events that tested not only his scientific intellect, but also his moral philosophy. The man who had spent his life exploring the mysteries of the atom suddenly stood at the center of a political storm that would determine the future of humanity. His discoveries, once symbols of enlightenment, now threatened to become tools of destruction. The age of quantum theory had given birth to the age of the atomic bomb, and Bohr, the thinker who saw science as a path to unity, was forced to confront the darkest consequences of knowledge. In the early years of the war, Denmark fell under Nazi occupation, and Bohr, already a world-renowned physicist, became a figure of great importance to both sides. His institute in Copenhagen was a hub of international research filled with students and colleagues from across Europe. But as the Nazis tightened their grip, scientific freedom vanished, and the city that had once been a sanctuary for thought became a place of fear. Bohr continued his work quietly, maintaining an outward calm, yet he knew that his Jewish heritage through his mother made him a potential target. The walls of his laboratory seemed to echo with tension, the same uncertainty that he had once described in his equations now surrounding him in life. In 1941, Werner Heisenberg, Bohr's former student and close friend, visited Copenhagen. The meeting between teacher and pupil has become one of the most haunting episodes in scientific history. Heisenberg, now working for Germany, spoke vaguely about atomic research, about the possibility of harnessing nuclear energy for a bomb. To this day, no one knows his true intention. Some believe he came to warn Bohr, others think he sought moral justification for his work. Whatever the truth, the encounter shattered their friendship. Bohr left that meeting shaken, realizing that science had crossed a boundary he had never intended. The atom, once a symbol of intellectual wonder, had become a potential instrument of annihilation. As Nazi pressure increased, Bohr's situation became untenable. In 1943, when Denmark's Jewish population was ordered to be arrested and deported, his family was in imminent danger. Friends within the resistance movement helped arrange his escape. In a small fishing boat, Bohr and his son crossed the narrow sea to Sweden under the cover of darkness. From there, he was flown in a British aircraft to England, his life literally hanging in the balance. During the flight, he sat in silence, the roar of the engines blending with the storm outside. Somewhere below lay the world he had known, a world at war, torn apart by the misuse of the very science he had helped create. When he arrived in England, Bohr was immediately drawn into the Allied nuclear effort. British and American scientists were racing to unlock the same power Heisenberg's team sought for Germany. Bohr, though deeply troubled, agreed to assist, understanding that inaction might hand the advantage to tyranny. He soon found himself in Los Alamos, among the brilliant minds of the Manhattan Project. Oppenheimer, Fermi, Teller, and others who wrestled daily with the paradox of progress. Bohr's role was not that of an engineer or designer, it was moral and philosophical. He urged his colleagues to think beyond victory, to imagine the world that would follow. He warned that secrecy and competition could only lead to future catastrophe. "We are in a completely new situation," he said, "that cannot be resolved by war." Yet his pleas went largely unheard. The momentum of history was too great, the machinery of war too vast. When the first atomic bomb was tested in the New Mexico desert, Bohr was not present, but he felt the shockwave in his soul. The brilliant light that tore through the dawn was both triumph and tragedy, proof of human genius and evidence of its peril. When Hiroshima and Nagasaki were destroyed, he mourned deeply, not only for the victims, but for humanity's loss of innocence. The atom had revealed its ultimate secret, and with it, mankind had crossed into a new and uncertain age. After the war, Bohr returned to Copenhagen with a mission that transcended physics. He began advocating for international openness and cooperation in scientific research. He believed that only through transparency could nations prevent the deadly secrecy that had fueled the arms race. His proposal, known as the Open World, urged governments to share nuclear knowledge under international control. He met with leaders, including Winston Churchill and Franklin D. Roosevelt, hoping to convince them that global peace depended on mutual trust. But the political atmosphere was already hardening into the Cold War, and his vision of openness was dismissed as idealistic. Still, Bohr refused to surrender his faith in dialogue. In speeches and essays, Bohr spoke of complementarity not only in science but in human relations. The need for understanding between opposing forces, whether they were particles or nations. He saw the world as a system of interconnected parts, where isolation led to imbalance and destruction. His experience during the war had convinced him that the survival of civilization required the same humility and collaboration that he had practiced in science. To Bohr, the lesson of quantum physics was clear: no single observer could claim the whole truth. Humanity, too, could not survive divided by ideology. In the final years of his life, Bohr's house once again became a gathering place for students and thinkers. He spoke often of the moral responsibility of scientists, how every discovery carried with it the weight of choice. The atom could illuminate or destroy, knowledge could unite or divide. What mattered was the wisdom with which it was used. He saw the younger generation of physicists not as heirs to his theories, but as guardians of a fragile future. He reminded them that science was not merely about power, but about understanding, an understanding that must be guided by conscience. Niels Bohr did not live to see the disarmament he dreamed of, but his influence endured. The principles he championed laid the foundation for future efforts at nuclear cooperation and arms control. More than any other scientist of his era, he understood that the discovery of atomic power was not an end, but a beginning. A moment when humanity was forced to look inward and decide what kind of species it wished to become. His journey from the quiet laboratories of Copenhagen to the storm of global conflict was a journey from theory to responsibility, from wonder to wisdom. Through it all, Bohr remained a man of profound humility, a scientist who never forgot the human heart behind the equation. He had glimpsed both the brilliance and the danger within the atom and within mankind itself. In the echo of the nuclear age, his voice still speaks softly that knowledge must serve peace, that openness must replace fear, and that even in the deepest darkness of war, the light of understanding can still be found. As the world emerged from the chaos of war and stepped into the atomic age, Niels Bohr turned his gaze toward the future. A future that demanded wisdom as much as it demanded knowledge. He had seen what scientific discovery could unleash when bound to secrecy and fear, and he understood more clearly than anyone that the next great challenge was not in the laboratory, but in the heart of humanity itself. The sixth stage of his journey was defined by reflection, a quest to secure the moral foundation of science for generations to come. It was no longer about equations or experiments, it was about creating a vision of peace rooted in understanding. In the years following 1945, Bohr became an elder statesman of science. He returned to Copenhagen, to the institute that bore his name, and sought to rebuild the spirit of cooperation that had once defined it. The walls of the building had survived the war, but the world beyond them had changed. The tension between East and West was deepening, and the Cold War had begun to divide not just nations, but scientists themselves. Laboratories that had once shared discoveries now guarded them with suspicion. In this climate, Bohr's voice rose as one of conscience, calm, deliberate, and deeply human. He reminded the world that the strength of science lay not in secrecy, but in openness, not in competition, but in collaboration. Bohr began drafting letters and papers that would become his moral testament to the world. In 1950, he addressed an open letter to the United Nations titled Open World, in which he urged all nations to share scientific knowledge transparently, especially concerning nuclear technology. He argued that mutual understanding was the only real safeguard against destruction. Every nation, he wrote, must be willing to renounce secrecy and contribute to a common security based on trust. It was a vision both idealistic and practical, born from his belief that the same principles guiding atomic structure, complementarity, interaction, and balance, should also guide human society. But his message met resistance. The world powers, trapped in the logic of deterrence, viewed openness as a weakness. Bohr's words were praised for their wisdom yet ignored in practice. Still, he persisted. In lectures across Europe and America, Bohr spoke of science as a bridge between cultures. He reminded audiences that the pursuit of knowledge was a universal human endeavor transcending borders and politics. To him, the laboratory was a symbol of unity, a place where language, race, and ideology disappeared before the shared mystery of nature. He often said that scientific progress required honesty and humility, virtues that could also heal the wounds of war. When young physicists visited him, he spoke not of glory or power, but of responsibility. Each generation, he would say, must learn anew that the greatest weapon we have is understanding. During the 1950s, Bohr's Institute once again became a center of intellectual exchange. Scientists from both sides of the Iron Curtain visited Copenhagen, drawn by Bohr's reputation for fairness and wisdom. The meetings were small, informal, and profoundly human. There, amid the books and chalkboards, dialogue replaced division. Bohr knew that he could not stop the nuclear arms race, but he believed that even small acts of communication were seeds of peace. In his quiet way, he became a diplomat of science, building trust where politics had failed. Though age had softened his voice, it had not dimmed his spirit. He continued to engage with the fundamental questions that had shaped his life. What does it mean to know? What is reality? How can knowledge serve life rather than threaten it? To Bohr, these were not philosophical luxuries. They were moral imperatives. He saw the atom as a mirror of human nature, where opposites coexist and balance sustains existence. Just as light could be both wave and particle, humanity too could be both powerful and peaceful, if only it learned to see itself from more than one perspective. As his health began to decline, Bohr spent more time reflecting on the legacy he would leave behind. He took comfort in the progress of international cooperation in science, the founding of institutions like CR in Europe, which embodied his ideals of shared discovery. He saw in these efforts the faint beginnings of the open world he had dreamed of. His final writings carried a tone of serenity, as though he had accepted that true change takes generations. "The road to understanding," he once said, "is endless, but every step forward brings us closer to harmony." Bohr passed away in 1962, but his influence continued to ripple through the scientific and moral fabric of the modern world. His students carried on his ideas, and his concept of complementarity extended far beyond physics into philosophy, psychology, and even politics. He had taught that truth was not absolute but contextual, that wisdom required embracing contradictions rather than denying them. In the uncertain world of the nuclear era, this insight became a guiding light, a call for humility in the face of complexity. Even decades after his death, Bohr's presence is felt wherever science and ethics meet. His portrait hangs in laboratories around the world, not as a symbol of power, but as a reminder of conscience. He remains the scientist who refused to separate knowledge from morality, who believed that the human mind must evolve alongside its discoveries. His legacy is not merely in the equations that bear his name, but in the way he reimagined what it means to be a scientist. A seeker not just of truth, but of peace, Niels Bohr's final gift to humanity was a vision of balance. In an age of extremes, he taught that understanding the universe begins with understanding ourselves. That every experiment, every question, and every discovery carries with it the duty to protect life. His life was a journey from the atom's heart to the conscience of civilization, and his message still whispers through time that the measure of progress is not in the power we wield, but in the wisdom with which we choose to use it. As the story of Niels Bohr reaches its final chapter, the world begins to understand that his life was never just about physics. It was about the evolution of human thought itself. He was a man who looked into the smallest building blocks of matter and found within them a mirror of existence. His final years were not filled with experiments or discoveries, but with reflection, teaching, and the quiet wisdom that comes only after a lifetime of seeking truth. He had become not just a scientist, but a philosopher of reality, one who had redefined how humanity perceives knowledge, uncertainty, and its own place in the cosmos. Bohr's impact extended far beyond his laboratory walls. His principle of complementarity, that seemingly opposing truths can coexist and complete one another, became a lens through which future generations examined everything from human psychology to political dialogue. He showed that contradictions are not failures of understanding, but essential features of the world itself. Just as an electron can be both a particle and a wave, people too can hold opposing views that together form a deeper truth. In an age torn by division, his idea became a quiet plea for unity, not through conformity but through comprehension. In the scientific world, Bohr's influence was profound. His students carried his vision into new frontiers, shaping quantum mechanics, nuclear physics, and even the birth of information theory. The Bohr Institute in Copenhagen remained a sanctuary of open thought, a place where the next generation of thinkers came to question, to challenge, and to wonder. His approach to science, collaborative, humble, and deeply human, became a model for research communities around the world. Even as technology advanced and experiments grew more complex, his spirit lingered that science was a dialogue, not a conquest. Yet Bohr's true legacy cannot be measured in theories or institutions. It lies in the moral compass he offered to science itself. He had seen how discovery could transform into destruction, how brilliance could be twisted by power, and in response, he gave the world a philosophy of responsibility, the idea that knowledge must serve life. In an era defined by nuclear weapons and political fear, he became a voice of calm reason, urging leaders to see beyond rivalry. His concept of an open world was not just a diplomatic proposal, it was a moral necessity. He believed that the survival of civilization depended on transparency, trust, and shared understanding, the same principles that govern nature's balance. As time passed, the echoes of Bohr's thoughts reached beyond science into art, literature, and even religion. Thinkers and writers began to explore his vision of reality, a world where certainty dissolves into possibility and truth emerges from perspective. He had, in essence, reshaped humanity's relationship with mystery. The unknown was no longer a boundary to be feared, but a space to be respected. To Bohr, wonder was not ignorance, it was the beginning of wisdom. This humility before nature became the moral foundation of modern science, a reminder that progress without reflection leads only to ruin. In his later years, Bohr often walked through the gardens near his home in Copenhagen, speaking softly to students who visited him. Those who met him described a man of serenity, with eyes that seemed to see beyond the moment. He rarely spoke of fame or recognition. Instead, he pondered questions of understanding, peace, and the human condition. He believed that the true challenge of the modern world was not discovering new facts, but learning how to live with what we already knew. In every conversation, he carried the same gentle insistence, that humanity's future depended on its ability to think together. When Niels Bohr passed away in 1962, the world mourned not only a scientific genius but a moral visionary. Newspapers across continents described him as the conscience of science. His funeral was attended by leaders, scholars, and students from around the world, each of them aware that an era had ended. Yet, even in death, Bohr's influence continued to expand. His principles became embedded in the structure of international cooperation in science, from CERN's collaborative model to the treaties that sought to control nuclear arms. The scientific community carried his torch forward, striving, however imperfectly, to live by his ideals of openness and responsibility. Today, decades after his passing, Bohr's vision feels more relevant than ever. In a world once again divided by ideology, competition, and fear, his call for complementarity, for understanding across difference, rings with renewed urgency. His belief that the human race must act as a single, interdependent system echoes in the global challenges of our time: climate change, artificial intelligence, and the search for sustainable peace. Each of these crises demands the same balance Bohr saw in the atom, a coexistence of opposites held together by understanding. Bohr's life teaches that science, at its best, is a moral journey. It is not the pursuit of control, but of harmony. The more deeply we peer into nature, the more we see ourselves reflected back, our conflicts, our hopes, our fragility. In this mirror, Bohr found both warning and promise. The warning was clear: unchecked power leads to destruction. The promise, however, was that knowledge, guided by compassion, could heal and unite. And so the legacy of Niels Bohr endures, not in the cold equations of physics alone, but in the warmth of his philosophy. He reimagined reality not as a battlefield of certainties, but as a dialogue of possibilities. His vision bridged the gap between science and humanity, showing that the greatest discovery is not what lies within the atom, but what lies within ourselves. In every generation of thinkers who dare to question, who seek not only to know but to understand. The quiet light of Bohr's wisdom still shines, reminding us that even in uncertainty, there is truth, and in truth, there is hope.